Welcome back. I have a structure here. You also have several parallel forces that are applied downwards on the structure. You know how to simplify this force system by choosing a point and putting there a resultant force and adding a couple moment to it. However, what if I told you that I would like you to replace this force system with a resultant force only, without a couple moment? Would you be able to do it? Can you replace these 5 force vectors with one resultant force only without including a couple moment? Try it out by yourself first and then see the solutions in the next video. Thank you very much. Welcome back. So let's figure out if we can replace this force system with a resultant force only without a couple moment. Let's first find this resultant force. It will be Fr equals all this times J. All these forces point down in the negative y direction. And so in the end you will have minus 4,500 J newtons. Of course, here you have 1 kilonewton, but that's the same like 1,000 newtons. And the same thing here, 2 kilonewtons, it's 2,000 newtons. Now here I have my point A, and let's calculate a resultant moment about this point A due to all these forces. So I have MRA equals minus 500 times 0, that's this force, but the moment arm here is 0 meters, then minus 1000 times 1 meter, so it's this force here, and this is your moment arm, minus 500 times 2 meters, so now we have this force, and we have 1 plus 1 meters. Then you have minus 2,000 times 3 meters, so it's this force, and now you have 3 meters till your point A, and finally you have minus 500 times 4, it's this force here, and you have 4 meters here till point A. The reason why they are all negative is because all the moments produced by these forces are going to be clockwise. And so in the end you will have minus 10,000 Newton meters. So right now I can replace this force system with an Fr that is 4,500 newtons and a clockwise couple moment which is 10,000 Newton meters. So right now these two systems are equivalent to each other. However, what if I now relate Fr and MRA with this equation? MRA equals Fr times D. Essentially, there is a special distance from point A such that if I place my Fr there, then it will give me this MRA. And it makes sense, right? Fr times D equals MRA. In our case, D equals MRA over Fr, so 10,000 Newton meters over 4,500 newtons. From the units you can see that the newtons get cancelled out, and you will have 20 over 9 meters, or approximately 2.22 meters. So if you put your Fr in this particular location, 2.22 meters from point A, then it is equivalent to having your Fr at point A with this couple moment. Only now you don't have to include this couple moment in the drawing because Fr creates it automatically by being 2.22 meters away from point A. Since they are equivalent representations of the force-moment system, it is also equivalent to the original case with 5 forces. In all the 3 cases, our rigid body structure will undergo the same behavior. Thank you very much. Welcome back. I have a wall here that is subjected to 3 forces in the negative y direction. The wall is on the xz plane. And now your task is to represent this system with one resultant force only, without adding any couple moments. So just like in the previous problem, you have to calculate a resultant force and place it in the right place on the xz plane so that it would become equivalent to this system here. So good luck, try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now replace this force system with a resultant force, and let's place it in the right place in order to skip adding the couple moment there. Let's first get the resultant force. It equals J times minus 3 minus 2 minus 5, that will be minus 10 times J kilonewtons. So I simply add up these 3 forces that all point in the negative y direction. And now we have to calculate a resultant moment vector about point O due to these 3 forces. We could use the traditional cross-product formula for 3D, where I have some kind of position vector and then I cross it with a force. However, it's not necessary here. All the forces are parallel to the y-axis, and they are all applied to the xz plane. It means that all the position vectors R1, which is this one here, R2, which is this position vector here, and R3, which is this position vector here, none of them have a y component. So the moments due to these 3 forces here about point O cannot have a component in the positive y or negative y direction. In fact, you can see that according to the right-hand rule. All the forces will cause moments about the positive x-axis and a negative z-axis. None of the forces will cause some kind of moment about the positive y or negative y-axis. There will be no moments about the y-axis. And so, the resultant moment about point O is the following. MRO equals I times 5 times 1.5. This is the 5 kilonewton force. And the moment arm from this force till the x-axis is 1 plus 0.5 equals 1.5 meters. And it's about the positive x-axis, so it's positive. Then plus 2 times 2.5. So now we are dealing with this force, and the moment arm till the x-axis is 1 plus 1 plus 0.5. So it's 2.5 meters. And finally you have plus 3 times 0.5. So we are dealing with this force and the moment arm till the x-axis is 0.5 meters. And again, all of them are positive because all of them create a moment about the positive x-axis according to the right-hand rule. And now we have plus k minus 5 times 0.5. So again, it's this force, but now it's 0.5 meters from the z-axis. Then you have minus 2 times 1.5. So it's again this force, and it's 1.5 meters from the z-axis. And then you have minus 3 times 1.5. So again, it's this force, and it's also 1.5 meters from the z-axis. And they are all negative because they all create a moment about the negative z-axis. And so if we add them all up, then we will have this result in kilonewton meters. And now I have to put my FR in the correct location on this wall in order to get my MRO. Essentially, I have to have MRO equals some kind of position vector cross FR. So this FR, it would be this one, this MRO, it would be this one, and then we would find this position vector here, the special position vector for this FR vector. But we can do it easier. Let's just treat X and Z dimensions separately. Again, we have this wall here. We know that the resultant force only has the negative y direction. It only has J. But the resultant moment has an I component and a K component. So let's treat all these components separately as scalars. So for example, I'm gonna say that FR times dz, so the distance in the z direction, from this point O, from the origin, it will give me the x component of this resultant moment. It makes sense, right? If this is my FR, and then this distance here, that's my distance in the z direction, then I will get a moment about the positive x-axis. And so my dz, it equals MROx over FR, so it's gonna be 14 over 10, and it will give me 1.4 meters. So this dz, it's 1.4 meters. And now I need to find my dx, the distance from point O till this special place for my FR vector in the x dimension. And if I write FR times dx, well, that will give me a moment about the negative z-axis. So in the magnitude form, I'm just gonna write here MRO z, which is 10 kilonewton meters, and so dx equals MROz over FR, so you have 10 over 10, which is 1 meter. So this dx here, it's 1 meter. And then you can see that there is no moment component in the y direction, which is why there is no need to calculate dy. So FR, that is in the negative y direction, and which is 10 kilonewtons, it causes a moment of 14 kilonewton meters about the positive x-axis if you place this force at z equals 1.4 meters, and then the same force will cause a moment of 10 kilonewton meters about the negative z-axis if you place this force at x equals 1 meter. As a result, this position vector r0, it will be 1i plus 0j plus 1.4k meters. Note that the most correct way to do it would have been to use the cross products and determinants. However, sometimes the problem is set up in such a way that you can simply use the right-hand rule and algebra to get the answers. That's usually the case when your forces only have one dimension, like in this case, and the objects that the forces are applied to, like our wall, they are completely perpendicular to those forces, which is the case here as well. But we can check if our R0 is correct. R0 cross FR, that would be this 3 by 3 determinant. And if you calculate that, then you will have I times all this minus J times 0 minus 0 and plus K times and then all this, and that will give you 14I plus 0J minus 10K kilonewton meters, which is your MR0. As you can see, the answer is exactly the same that you have here. But now, let me ask you a question. Imagine that you have FR on the XY plane, and then MR0 has all the X, Y, and Z components. So MR0 is not perpendicular to FR in any way. Can you now place FR somewhere in a 3D space to make MR0 disappear? The answer is no. FR needs to be perpendicular to MRO, just like it was in this wall problem, where FR was in the negative Y direction, and then MR0 was on the XZ plane, where one component was in the positive X direction and the other component was in the negative Z direction. And both components were perpendicular to this FR force. Or like in the bridge problem, where FR was in the negative Y direction and MRA was in the negative Z direction. So the arrow goes into the screen away from you. Again, here both vectors are perpendicular to each other. If that's not the case, then you can only simplify the force-moment system if you use both FR and MR, both the resultant force and resultant moment. In this case here, you cannot get rid of your couple moment. You can try it out. Let's say that FR equals 2I plus 2J plus 0K, and let it be in newtons. And then MRO equals 2I plus 2J plus 2K Newton meters. So you can see that they are not perpendicular to each other. So if you try to find the position vector RO with this formula, RO cross FR equals MR0, then you won't be able to find it because it doesn't exist. But you can try it out anyway. So this cross product here, it would give you this 3 by 3 determinant. So this one here, that's your FR, and this is your position vector, your RO, which is what you're looking for. And so all that equals I times all this minus J times all this and plus K times all this. So you will have all that, which equals your resultant moment, 2I plus 2J plus 2K. So this one needs to equal this one, then this one needs to be this one, and then this one needs to be this one. And now you need to find the position vector components, your unknowns, Rx, Ry, and Rz. And so in the first case, we have minus 2 Rz equals 2. That's this case. It means that Rz equals minus 1. And now if we take another case, the J case, then you have 2Rz equals 2 and Rz equals 1. So there is no point to continue because you can see that you get Rz equals minus 1 and Rz equals 1. And it obviously doesn't make sense, which means that there is no solution for this case. If FR and MRO are not perpendicular to each other, then you have to add an additional couple moment with your FR vector when you simplify your force moment systems. Just like we did it with this beam exercise some videos ago, and the pipe exercise that we also had some videos ago. Over there we had both FR and MRO. Thank you very much.